Today, we're diving into a really fascinating intersection of physical motion and mathematics. We are talking about distance time graphs. We're essentially going to learn how to decode these visual maps, exactly like a detective reading visual clues at a crime scene. And to do this, we're going to follow a totally relatable story about a girl named Tisha and her somewhat chaotic morning commute to school. So, get ready to look closely at the evidence, and let's jump right in. So, picture this. It's morning, and Tisha leaves her house. She starts out walking at a nice, constant speed. Walking steadily, she's not speeding up, she's not slowing down. For the first 6 minutes of her commute, she covers exactly 540 meters. But then, as it always goes, she spots her best friend on the sidewalk. They stop right there near a corner shop and start gossiping. They stay completely stationary for 2 whole minutes, not moving an inch. Then, panic mode. They suddenly realize they are super late for class, so they start speed walking, covering another 240 meters in just 2 minutes. Now, you might be wondering, how do we take that chaotic, real-world physical journey and actually turn it into a clean, mathematical picture? Okay, let's dive into this. Before we draw anything at all, we've got to organize the raw physical actions of Tisha's journey into a clear data table. Let's break it right down. At time 0, Tisha is still at home, so her distance from the start is, 0 meters. After 6 minutes of that steady walking, she's traveled 540 meters. Then, for the next 2 minutes, she's stuck in exactly the same position, because she's chatting with her friend. So at the 8-minute mark, her distance is still stuck at 540 meters. Finally, she kicks it into high gear, adding 240 meters to her trip, meaning she hits a grand total of 780 meters right at the 10-minute mark. All right, now we can start translating this structured data into our visual graph. In any distance time graph, the horizontal axis, the x-axis, is what anchors our whole story. It represents time. And you can see how time flows continuously across the bottom, from 0 minutes to 6 to 8, and finally to 10. Time always marches across the bottom. Working right alongside that, we have our vertical axis, the y-axis. While that bottom axis is tracking the flow of time, this side axis is tracking total distance. It rises vertically up the side to show exactly how far Tisha is from her starting point, peaking right at her final distance of 780 meters. So time on the bottom, distance up the side. Section 1. Plotting the graph, connecting the dots. Now, by just taking our table's coordinates, 0 to 0, 6 to 540, and so on, and connecting the dots, we literally reveal the exact visual shape of Tisha's motion over time. So, what is this newly drawn shape actually telling us? Well, here is the absolute most crucial mathematical concept you need to know: slope, or as it's often called, the gradient. The slope visually represents speed. The steepness of the line tells us exactly how fast our object is moving. Think about it like climbing a hill, right? A steeper climb means you're rising a lot more quickly. It's the exact same on our graph. A steeper line means distance is increasing very quickly, which means a higher speed. Let's apply this visual rule to the first 6 minutes of Tisha's graph. See how the line rises straight upwards diagonally? This is super important. Because that line is straight and diagonal, it mathematically tells us that Tisha is moving at a perfectly constant speed. She isn't speeding up and she isn't slowing down. She's just walking steadily along. But then, we hit the really interesting part of the story. From minute 6 to minute 8, look at what the line does. It goes completely, totally flat. Time is ticking forward on the bottom, but the distance isn't rising at all. In the real world, this horizontal line proves without a doubt one thing. Tisha is completely stationary. The graph is literally showing us that gossip session. Now, boom, look at what happens right past that 8-minute mark. The line rises again, but look at the visual shape here. It is noticeably steeper than it was in the very first section. So what did our detective rules say? A steeper line means a faster speed. Tisha is moving way faster because she's in an absolute rush to get to class. That sharp steepness is the perfect visual clue. Okay, so we've mastered the visual side. We can literally just look at the steepness of a line and instantly know if someone is walking steadily, standing still, or full-on rushing. But what if we need to know the exact numbers? How do we transition from just eyeballing that visual steepness to figuring out the hard math behind the gradient? Well, to calculate the exact speed, we just need to decode that gradient. And honestly, the formula is as simple as following a recipe. Step 1, find the total change in distance. Step 2, find the change in time. Step 3, just take that distance and divide it by the time. That's the whole shebang. Speed simply equals distance divided by time. Let's actually do the math for Tisha's journey to see this in action. During her first steady walk, 540 meters divided by 6 minutes gives us 90 meters per minute, right? Now, let's calculate that final panic mode section. She covered 240 meters in 2 minutes. So 240 divided by 2 is 120 meters per minute. Wow, she was seriously booking it. And this brilliantly illustrates our visual rule. 120 is higher than 90. And sure enough, that final line is visibly steeper on the graph. The math completely backs up our eyes. Real quick before we finish up our investigation, I want to give you one more visual rule. What if you see a line sloping downwards? Well, a downward slope just means the object is returning toward where it came from. And if that line goes all the way back down to touch the bottom x-axis, it means they've returned entirely to their absolute starting point. All right, let's do a rapid-fire recap of all the visual clues we cracked today so you can confidently decode any distance time graph you ever come across. Ready? The horizontal x-axis is time. The vertical y-axis is distance. A straight diagonal line means constant speed. A steeper line means faster speed. A perfectly horizontal line means completely stationary. A downward line means returning. And you can always find the exact speed by dividing the change in distance by the change in time.
And honestly, that is how you read a journey like a true detective. I really hope you enjoyed this explainer and that distance time graphs feel like a breeze to visualize now. Thank you so much for exploring this with me. I want to leave you with this final kind of funny thought. Next time you're out walking and you see someone just stop dead in their tracks to check their phone, literally imagine a flat horizontal line appearing right above their head. Thanks for hanging out and keep visualizing the math in the world around you.